Hi, everybody. Welcome to this My Data Guest episode. Today, we are going to learn how to build an AI agent using LangGraph. And for that, we have here Miguel Otero Pedrido. He's a machine learning engineer. He's a deep machine learning engineer. He's really devoted to being a machine learning engineer. And he's the founder of the Neural Maze community on Substack.
Hello, Rosaria. It's a pleasure to be here again because to be honest, I think I've been here two times.
That's the third time, yeah.
Yeah. One with Alessandro and yourself, with Josh and Luis.
Yeah, in the panel.
And yeah, this is my third time. So really, really excited to be here.
Yeah, you're a regular. Okay, let's start.
Okay. So yeah, today I'm going to present you a workshop about how to build agents with a pretty well-known framework for AI agents, which is called LangGraph. And to do that, I have prepared some resources. So I'm just going to share the screen. Okay, here it is. So right now, I'm just sharing the slides I'm going to use for this workshop, just so that you know that it's going to be hands-on. Then we're going to get into a Jupyter Notebook, a Google Colab, and it's going to be really code-focused because that's what I want you to extract from this workshop. But before, I want to give some context about what is an agent and what is LangGraph, etc. So I always like to start these kind of workshops with the six levels of autonomy. This is something that the creator of LangGraph, Harrison Chase, introduced like 1 year ago, and it basically tells you how LLM applications are going to be layered nowadays. So first of all, this is kind of naive, but we have like traditional coding applications. This is something that we are going to cover today because we've been doing this for a lot of years. Then we have simple LLM calls. This is something, for example, that you might be doing when you interact with ChatGPT. Then we have chains, then routers, state machines, and autonomous. And if you check the diagram here on the right, you can see the different levels of autonomy. Like, is this step deciding the output of each one of the steps? Is this layer going to decide which steps to take? And is this layer going to decide what steps are available to take? You can see that when we are progressing towards the bottom of the page, you will see that more and more things are delegated to the system. By the end, but this is something that we are not going to implement today. And to be honest, I don't think there is any system nowadays that is truly an AI agent, like a truly autonomous one. So we are going to keep here in the state machine because we are going to let the agent decide the output of this step because we are using an LLM, and we are going to decide which steps to take. So the agent is going to decide which route to take. This is basically a bit of a deep dive into each one of the levels. As I was saying, the first level is just coding. Then the second level, which is we have an input prompt and we have a response. The third level, which is the chains. This is the original intent of LangChain, which is like the precursor library of LangGraph. And LangChain is just lets you create these chains, which are steps composed one after the other, which you have a start, an input, and then an output. Then we have the router pattern. This is something that I'm going to explain you in a few minutes in the notebook. And in here, the only difference with the chain is that the LLM has the ability to decide between different paths based on the previous step. And then higher levels, the fifth and the sixth level, are just pointing the direction of semi-autonomous, in the case of the fifth level, like the router, or fully autonomous, where we have feedback loops, where we have like a fully autonomous agent. So before we get into the code, there's something that I also want to highlight, and is that even if we have really fancy patterns, really fancy architectures like the router, etc., an agentic system needs memory. And there are two kinds of memory, short-term memory and long-term memory. Short-term memory is also known as the working memory, and it refers to all the context available to the LLM at the time of generating the response. And this diagram in here, it's becoming more and more popular. It's the context engineering diagram. Basically, it's all the things that you're putting into the context of the LLM when the LLM generates a response. Might be the state, like the history of messages, retrieve information, long-term memories, user prompts, available tools, etc. Right? So that's like the working memory. And then we have this long-term memory, which might seem misleading with the long-term memory here, but it's something a bit different. In this case, we are just talking about that kind of context that is located outside of the LLM. For example, in a vector database like Chroma. And I put here Chroma, this vector database, because this is the one that we are going to use today, but you could use any other vector database that you want. And now let's get into the main protagonist of this workshop, LangGraph. And what is LangGraph? So LangGraph is a framework for AI agents, and it's designed for building complex and stateful LLM agent architectures. And this is really important, the part of the stateful, because you will see that in LangGraph, we are defining a state and the different nodes and edges connected to each other. That's the reason for the graph in the name. As I was saying, LangGraph uses a graph-based architecture that gives developers like fine-grained control over agent behavior. And this is something important because for some applications, you might want to go with Crew AI or any frameworks which are more like high level. If you want to have more control to build more customizable solutions, LangGraph is probably your best pick. And yeah, it's also ideal for creating robust production-ready AI systems. This is whenever I implement something for a client or even for my company, we try to do it in LangGraph because it feels really well with production systems. All right. And now let's get into the code. So as I was hinting you before, Rosaria, today, just going to show you how to build a React agent connected to a vector database, everything done using LangGraph. And this agent will answer questions about articles from my data guest Substack. So we are going to inject the information about one of your articles, Rosaria, and the agent is going to answer some questions with a short-term memory and also with a couple of notes. It's going to answer some questions about your article. And in here you can see more or less the diagram of the architecture that we are going to build. So first of all, we are going to take your article, one of your articles from Substack. We're going to create embeddings and insert them into ChromaDB, into the vector database. And then our agent is going to fetch this information. It's going to fetch this information and answer our questions, basically. Okay, so now let's go to the actual code. So first of all, I just structured this as the following. The first block of this notebook, this is also something that I'm going to share with you, but the first block is going to be devoted to understanding LangGraph structure and the different building blocks necessary to build a LangGraph workflow. So as I was saying, we are going to start with understanding the basics, the building blocks of any LangGraph workflow or any LangGraph graph. So first of all, we're just going to install some libraries. To give you a quick overview, we are installing LangChain OpenAI because we are going to use OpenAI models, LangChain Core because some of the building blocks that we are going to use are coming from LangChain Core, LangChain Community for some of the connectors that we are going to implement, LangGraph, as it's obvious, and finally LangChain Chroma, and this is a connector to connect our workflow, our LangGraph workflow, with the Chroma vector database. All right, so as I was saying, let's start by understanding the fundamental components from LangGraph. And these are three. First of all, we have the state. Every LangGraph workflow that we build starts by defining the state of this graph. And this state can persist any kind of information. It can persist the output of each one of the nodes at any stage, locate as well like the history of messages, anything that you are sharing inside the graph. All of that is going to be persisted inside a state. Okay, so this state is defined as a typed dict in Python, but you will see that there are clever ways inside LangGraph to just import already like pre-built states that take care of you to append messages to a list of history messages, etc. So we are going to start by defining this state. Really, originally I've named state, and then we are going to the second building block, nodes. So nodes are just Python functions. Each node takes the state of the graph, of the workflow, of the LangGraph workflow at that point, and it just modifies that state. It might be adding a new property. It might be updating a property, an existing property on the state, whatever. So it just takes the state and it returns an updated state. In here, I'm just defining the most stupid nodes ever because they are just taking a state, which is a string, and just going to update the string. And in here, we are you can see that node 1 is just going to add to the existing graph state welcome. This is going to take the existing graph state and add to the data hack summit. This is because part of this demo is from the summit that I did with Alessandro in Bangalore. And also here, the graph state is just going to modify in a different way the state of the graph. Okay, so just to keep it clear, each one of these nodes is taking the existing state and providing some changes in the state. And lastly, since we have a state and nodes, we need a way to connect the nodes with each other. And we do it by using edges. There are two kinds of edges: normal edges and conditional edges. Normal edges are used when you always want to transition from node 1 to node 2. Conditional edges allow for dynamic routing between the edges. Depending on different conditions, you can route from node 1 to node 2, or depending on this condition, to node 3. And this is something that you can see here. Here we are just defining this decide node, which is a function that will trigger which node to go from node 1, either node 2 or node 3. And this is just based on this random generator, right? So if it's less than 0.5, we are going to route to node 2. If it's more than that, we're just going to route to node 3. So this is a dynamic node. Finally, we have the state, we have the nodes, and we have the edges. It is time to build the graph. And you will see that this is really easy. I'm just going to go through code. But LangGraph at first is a bit weird in terms of how things are defined, because apart from the state graph, this is something that creates the LangGraph builder that we are going to compile to create the actual LangGraph workflow. You will see that I'm also importing from LangGraph graph this start and end nodes. This is not something that I have implemented. This is necessary in any LangGraph workflow to define the start and the end of your workflow. All right. So you always need to import and to define the start and the end inside your graph. And I will show you how to do it. So the first line, we are creating a builder. We are passing our state that we're defining here, the state that we define here. We are just passing to the state graph creator. And this is creating this builder. After that, we are just adding the nodes, node 1, node 2, and node 3. And finally, if we stopped at this point, we only have like 3 nodes, but with no interconnections. We need to connect the different nodes with each other. And that's where we start defining the edges. So first of all, remember that we always need to tell LangGraph where everything starts. So we need to start with the start node, and this node is going to be connected to node 1. We are using this at edge. We are also defining the conditional edge. Remember that is going to route between node 1 and node 2 or 3, depending on the random condition we're defining here, but you could create any dynamic routing that you want. And to do that, we are just using the add conditional edges, node 1, and the condition function. And finally, we are adding normal edges between node 2 and the end, and node 3 and the end. All right. After that, we are just compiling everything. So we have the actual LangGraph graph. And here, this is just a fancy function that you can use if you want to display everything like this. Okay, so this is what LangGraph is going to run whenever you invoke the graph. You can see the start node that is going through the node 1, and then depending on the condition, it could go through node 2 or node 3. But both node 2 and node 3 are going to be connected to the end node. All right, in terms of execution, I don't know if the audience is familiar with LangChain, but it's pretty similar to everything that works on LangChain, just using this invoke method. Every class, almost every class in LangChain and also in LangGraph implements an interface that allows you to invoke, like calls to these interfaces using the invoke method. And in here, we're just invoking our graph with an initial state. This is really important. When you're working with LangGraph, you need to forget about the traditional way of doing things, because what you are inputting is a LangGraph state, and what you're receiving back is an updated state. So we need to start thinking in terms of states and graph to understand LangGraph. And in here, I'm just saying graph state, hi there, it's Miguel. And based on, this is a random function, remember, that is going to route to different nodes. In some cases, it's going to say, welcome to the DataHack Summit. In other ways, it's going to say, welcome to Bengaluru, because remember that in here, we are just routing to different places depending on the random function. All right, so now we have an idea of the 3 building blocks of LangGraph. Now it's time to start building cool LLM applications with LangGraph. And by the end of this notebook, we will be able to create this React agent expert in my data guest. So building LLM applications with LangGraph. I just want to raise again this slide about the 6 levels of autonomy in LLM applications, because we are going to start with the chains, well, with the LLM calls and the chains, then we are going to go to the bottom of the page to get to more agentic solutions by the end. So in terms of chains, so to build a simple chain, remember, it's just a concatenation of different nodes or different blocks. We are going to use these 4 concepts. So first of all, we need chat messages. This is just a fancy abstraction that LangChain and also LangGraph provides to access to interact with LLM providers. OpenAI, Claude, Gemini, whatever you want. We are using chat models inside graph nodes. Remember that nodes are just Python functions. We will see it later. And we are just putting all of this logic for making the calls to the LLMs inside the nodes. We are going to bind tools to our chat model so that our LLM is able to call Wikipedia or to, use a calculator. And finally, we are executing tool calls in graph nodes as well. All right. So let's start with the chat models. And first of all, understand the kind of messages that LangChain and also LangGraph use under the hood. There are 4 types of messages, right? We have the human message. This is a message from the user, from the human. AI messages from the chat model. System messages to guide the model's behavior, the typical system prompt. And tool messages, which are coming from a tool. And here, I'm just making a really quick experiment in which I'm passing a list of messages. The first one is an AI message that says, "Hello, I'm the virtual assistant for my Data Guest podcast. What can I do for you?" And the name is Agent. And then we have another human message that says, "I'd like to know more about Rosaria Silipo." I don't know if that's pronounced correct. And here you can see how it looks like. We have an AI message and a human message, just a list of these 2 messages. And now, well, first of all, we are just setting the OpenAI API key. And now we're just making an invoke to the LLM, to the chat OpenAI. I'm using GPT-4o, but you could change it to whichever you want, and just making an invoke with the list of messages. So it should provide a good following up of this conversation, right? Okay, so let's see what it says. So we are generating the result. And here we can just plot the content. So Rosario Silipo is a well-regarded data scientist with extensive experience in the field of data analytics and machine learning. She has a strong academic background, blah, blah, blah. You can point out whatever you find inaccurate, Rosaria. Okay, so we can see how the list of messages is working and how chat models work. I mean, it's just one line of code, and you can access all the functionalities of OpenAI models. You could do the same for Grok or for whatever provider you decide to use. Now we are getting into the tools, and tools are really necessary if you want the LLM to get outside the model weights. Everything that it has learned through pre-training, we need a way for the LLM to access the outside world. And we achieve that by using tools, all right? It's really easy to bind tools to an existing LLM in LangChain and also in LangGraph. You just need to use this bind tools method that is already included in the chat model. So in here, just a really silly function that multiplies 2 integers, A and B. What we are doing is just binding the tools, which in this case is just one tool, but you could bind multiple tools. We are binding the multiply tool with LLM. And then we have an LLM with tools. So we could start invoking these LLMs with something unrelated to any multiplication operation, and it will just provide a regular answer. But it might be the case. So yeah, no tool call, pretty print, and hello, I'm just a computer program, because I'm just saying, hey, how are you? What happens if I make a mathematics statement, like what is 2 multiplied by 3? So in this case, the LLM is just going to understand that this is something that requires the tool, the multiply tool. What we are getting is not a message, but a tool call. And a tool call is just an object that LangChain and LangGraph use under the hood to define the function that we want to use and the arguments that we are going to pass it. Then we will need to take all of this information and make the proper call to the function, to the multiply function with 2 and 3 as arguments. But don't worry, because LangGraph allows you to make this automatically inside the graph. All right, so now I'm just going to show you a cool thing to define states in which we don't need to use the type dict that I showed you at the beginning. LangGraph already implements a way that lets you create a property inside the state that is going to allocate all the different messages, like the history messages between the user and the assistant. And this is really handy when you want to deal with short-term memory, because that's the only way in which the agent or the LM is going to remember the conversation with the user. So from now on, we are going to use this messages state. By the way, here, I'm just implementing it from scratch, and you can see here that LangGraph already implements it. So we are going to use this default implementation. Okay, and now that we have the LLM with tools that we defined previously, right, in here, just going to show you how you can add this information, how you can add this LLM with tools inside your graph. So in here, I'm just defining one node, which has the tool calling LLM that is receiving as a state. Remember, every node receives a state and returns a updated state. So as a state is receiving this messages state, okay? And this is the one that we define in here that contains a property for all the history of messages. So what we are doing is updating the messages property by just invoking our LLM with tools that we defined previously, all right? We are passing the current list of messages and we are updating the messages with the latest interaction, right? Okay, and as always, we are defining the builder with the state graph. We are adding just one node, the tool calling LLM, and we are defining the start and the end nodes, and also edges that connect the start with the tool calling LLM and the tool calling LLM with the end. We compile and we check if everything looks correct, which it does, just one single node. And now we have successfully implemented our first chain, which is super simple. But for the next examples, this will be really handy. So now we can simply invoke our graph with a human message, like for example, hey there, I'm Miguel, pretty similar to the experiment we did with the LLM with tools. And now let's do the same, but asking something related to multiplications, right? So we are invoking again our graph, and in this case is returning a tool call. So multiply 10 and 3, and the tool call is just telling us, okay, you need to take the multiply function and pass the args 10 and 3. Okay, so now that we understand how chains work, it's time to understand how the router pattern is implemented, because this is going to be really handy when we get to the React agent. And as I was saying at the beginning of this workshop, the router is just a tiny change or a tiny improvement from a chain, because it's just going to let the LLM decide which route to take, which path to take, depending on some condition. Okay, so we are going to extend the chain example, as I was saying, by doing two things. First of all, we are adding a node that we call our tool, and we are going to add a conditional edge that will look at the chat model output. And if it's a tool call, if it's of type tool call, it's just going to route to our tool calling node. And if not, it's just going to return a regular response. Okay. So yeah, here I'm just defining again the multiply in case you restarted the notebook or whatever. GPT-4o is our LLM, and we are binding the tools as we did previously. It's just the same code. And now we are using another fancy addition from LangGraph, which is the tool node, all right? And this tool node is the one that is going to take care of not just detecting that we need to use multiply with the arguments 10 and 3, as we did in here, but to actually take the multiply function, pass the arguments, take the result, and this result will be appended as a tool message into the history of messages, right? That's exactly what we want. Okay, and to do that, we are just, this code defining the tool calling LLM node again, and we are generating the builder with the state graph and the messages state, and we are adding a node that's going to connect the tool calling LLM with, we are adding the tool calling LLM node and this tool node, and this is the important thing, this is the difference from the single chain, because in here we are using this tool node and passing the tool inside, okay? And LangGraph internally is going to take care of all the management of this tool, which is really cool because you don't need to bother about managing tool calls, etc. Everything is done for you. Then we are defining the edges. So first of all, defining the start that is going to be connected to the tool calling LLM, and then a conditional edge that is going to take the tool calling LLM and is going to be routed differently depending on this tool's condition. And this is also something that we are importing from LangGraph. The tool's condition performs exactly what I was saying in here. This conditional edge that will look at the chat model output and route to our tool calling node, or simply end if no tool call is performed. This is exactly what we are achieving with the tools condition. Okay, so now if we run this cell, you can see how the graph actually looks like. So we start the tool calling LLM. Right now, there's a dynamic route, a dynamic edge, because if there are no tool calls involved, it's going to connect directly to the end. If there are tool calls involved, then it's going to get to the tool node, which is executing the tool and fetching the relevant information, and then sending this back to the end. Okay, so now let's invoke our graph, and you will see a difference from before, because now we have 3 types of messages. We start with the human message, which I'm asking, hello, what is 2 multiplied by 2? And we have this AA message, which is a tool call. But now we have this tool message, which is the actual result of the multiplication of 2 by 2, right? And this is exactly what we are going to attach to our history message, so we can, the LLM is able to respond, hey, it's 4. Okay, so now that we know about the chains and we know about the route pattern, it's time to attack, it's time to understand the type of architecture that is being used by 99% of the agents out there nowadays, which is the React architecture or the React design, or whatever we want to call it. But the React pattern is also an accurate naming. I'm just going to show you with this diagram that I created, because React is just a loop. Even if it sounds like super fancy, the name, whatever, it's just a pretty simple loop. And React stands for reasoning and act. What this loop does is it starts with an input prompt, like what is 2 plus 2, for example, and the LLM is going to think about what to do with this information. Then it's going to take an action, which might be calling a tool. Then it's going to execute that tool and observe the output of this tool. And once it does, it's going to pass the output of this tool to the thought again. And the LLM is going to say, okay, given the information that I've received from the observation, is this the final result, or do I need to call another tool? So you get the point. With React, we are able to call n different tools, and this loop is going to be executing until we get a response for the user. And that's exactly what we want with React. So in this case, I've just expanded our example from before. And now instead of having 1 tool, we have 3 tools: the multiply, the add, and the divide tool. Let's bind the 3 tools to our GPT-4o. Okay, so we are just binding our 3 tools that we defined here. And now I'm just adding this system message, by the way, that we haven't used previously, but system message is like a system prompt that's going to define the overall behavior of your LLM. And in here, I'm just creating a different state, right? Okay, now let's get to the actual compilation and building of the graph. So we start as always, same imports as always. We start with the state graph, we define the builder, we add the node, which is the assistant. Remember that we define it in here. It's just a single invoke with the LLM with tools. We are adding our tools node, but in this case, we are not passing just 1 tool, but multiple tools, right? 3 tools: add, multiply, and divide. And now let's create all the edges, right? Connecting start with the assistant and a conditional edge with the tools condition. Finally, and this is really important, this is just the only step that you need to implement React. It might seem like really complex when I explain the loop, but you will see that the only thing that we need to do is to close the loop by pointing back the tools node to the assistant node. That will be much clearer when I run this cell, because you will see the actual workflow. So you can see the start, the assistant. And now if the question is not related to any kind of mathematical operation, it's just going to get directly to the end. But if it is, it's going to call the tools, and the result of the tools is going to be sent back to the assistant. This is exactly what I was explaining here. Okay, we are closing the loop. So the observation, the actual output of the tool is going to be sent back to the context of the assistant. Okay, and here I'm just trying it out really easily. So add 10 and 5, multiply the output by 2, and divide the output by 5. We are just creating the messages in here. And finally, just checking that it works. You can verify the math, but it's fairly simple. So first of all, it's just adding, creating the first call to the tool. Then it's just calling the multiply tool, and finally the divide tool. And then just taking the output of the divide tool and say, okay, this is exactly what the user was asking to. So I'm just going to generate a regular response, which is an AA message. The result is 6. Okay, we are just getting close to the final system. Right now, we have a pretty decent understanding of the different designs, router, chains, now the React agent, but one thing is missing. And the thing that's missing is memory, because what happens if I take the previous graph, okay, and I introduce myself. Okay, hello, I'm Miguel. So our graph is going to say, hello, Miguel, how can I assist you today? All right, but what happens if I ask my name again? Okay, so we have a problem because our AI assistant has no pretty good memory. Okay, so I'm sorry, but I don't have the ability to remember personal details. So what is happening? The problem is that we have no short-term memory. We are not collecting, we are not compiling any checkpoint that is able to save the different interactions between the assistant and myself. Happily for us, it's really easy to add memory, to add short-term memory to our LangGraph workflows. And the only thing that we need to do is to use the module checkpoint from LangGraph. Okay, so LangGraph, checkpoint, memory, and memory saver. This is the in-memory saver of LangGraph. You could implement memory savers for SQLite, for Postgres, for Redis, for whichever database that you want, because at the end of the day, what we are going to do is just store the state of the graph, right? That's exactly what we are storing inside these checkpointers. So in here, what I'm doing is just creating this memory saver instance and compiling my graph with the checkpointer as argument. And as I was saying, the checkpointer is just going to write the state at every step of the graph. These checkpoints, apart from that, are going to be assigned to a thread ID. This is really important. If you are deploying this to a production service, you're building an application, you need to make sure that each user is assigned to a different thread ID, because that's the way in which LangGraph is going to track the different conversations. And we can access that thread in the future by using the same thread ID, right? If we go to the next cell, you will see that apart from the messages and the invocation, I'm also adding this configuration. And this configuration, this configurable thread ID, is the place where we are defining the thread ID. If I start a conversation with thread ID equals to 1, and tomorrow I open again this notebook and I use the same thread ID, the assistant is going to act like we spoke 1 second before. If I change this and I put here 2, then it's going to act like it did at the beginning. So I don't know who Miguel is. So we are going to try the same experiment that we did at the beginning. So I'm introducing myself here. Hello, my name is Miguel, but with our graph memory, with a graph with the checkpointer. And now let's see if the assistant remembers us. So can you say my name? Do you remember it? Now it does. So yes, your name is Miguel. How can I assist you today? This is a great step, because otherwise our agent would be completely a disaster. So now we have memory. And now we are adding something really fancy, which is in the field of long-term memory. We are going to attach a vector database to our LangGraph workflow. We'll use this long-term memory, this vector database, as a way to store external information. In this case, I'm just going to store one of Rosaria's articles on Substack, but you could use it for storing PDFs, for storing whatever you want. But I'm just going to use it to store one of Rosaria's articles. I'm using, by the way, as vector database, ChromaDB, but as I was saying at the beginning of this workshop, you could choose Quadrant, VB8, Pinecone, whatever you want. But ChromaDB works really well in a Jupyter environment like this one. That's the reason why I decided to do it. Before I get into the actual code of how to ingest the Rosaria's article and how to fetch the relevant information, the contextual information inside the agent, it's important to understand that this retrieval is made, this RAG, retrieval augmented generation, is made in 2 steps. The first step is indexing. And this diagram depicts really well what is happening when we are indexing our database. We are just loading our documents, taking, as you will see, this article from Rosaria, from my data guest Substack. I'm just splitting the article into multiple chunks, into little pieces. Then I'm embedding each one of these pieces with an embedding model and turning each one of these pieces into an embedding, into a vector. And finally, we are storing these vectors inside ChromaDB, inside the vector database. Okay, so this is the code that is going to instantiate both the embedding model, the LLM that we are going to use, and the vector store and the vector database. As embedding models, we are using text embedding 3 large from OpenAI. Since we are using OpenAI models, you could use Hugging Face embeddings or whatever you want. Chat model GPT-4o, because that's the one that we've been using. And vector store, you just need to use Chroma, which is a class that you can import from the launching Chroma connector. And in here, you just need to define the collection name, example collection, embedding function, with passing the embeddings model, and finally, where to persist the vector database. Okay, so I'm just putting here long-term memory DB. And as I was saying, you could even connect your Chroma class to external Chroma instantiations, for example, if you have it in a server in Amazon or whatever. All right, so now that we have everything, let me run this cell. Now that we have everything instantiated, it's time to download the article, Rosaria's article from my data guest, and apply the character splitter. Just take Rosaria's article and split it into multiple chunks. We are going to use the web-based loader from the LangChain community, document loaders. We are passing the URL, and we are just doing some beautiful soup ninja skills here to just take the content that we want. So in this case, I'm just focusing on the available content from the article. We're just loading the document, and we are applying the recursive character test splitter, which is one of the most common. And I'm just passing some defaults in here, but you could tweak this if you want. And then just generating the splits, generating the different chunks. If we run the Excel, you can see some of the chunks, and this is the first split. So how ChatGPT speaks on many languages, a quick overview of datasets, emergent behavior, and tokenization by Rosaria Selipo, which is just the beginning of the article. Okay, so it seems to be working fine, but let's find out what happens at the next step. Now, the only thing that is missing in the indexing step is to actually ingest all of these chunks inside the vector database, and that's what we are doing here in the last cell. Now we are going to the retrieval, which is the cool part, because this is the place in which the LLM or the agent is going to decide which context, which information from the vector database to fetch and to inject into the context. All right, so to do that, let me show you first of all, well, this command, this method that allows you to perform similarity search. At the end of the day, this is what you want from a vector database, all right? So you have the vector database, and you're just running this similarity search. And we are looking for something similar to do similarity search on this string, on this emergent behavior. At the end of the day, this is what we want the agent to do. The only difference is that this command, this cell, is just going to fetch the most similar chunks. But this is useless if you send it to a user. The user is going to be like, okay, but what is this? I mean, emergent behavior, and I see here like some chunks of text without any order, etc. We need to find a way to inject this into the LLM context. So the LLM takes all of this context and provides a clean answer and a structured answer to the user, right? But we can check nonetheless that it seems to be related. So emergent behavior in here describes skills or patterns that weren't directly trained into the model but appear as byproduct of its scale. So these are words of Rosaria Selipo. So if we keep going, we are just going to create a tool. Remember that our agent is able to access the outside world throughout tools. So we need to find a clever way to turn this similarity search, these vector database queries, into actual tools that the agent can use. And we are doing that using this create retrieval tool. All right. The create retrieval tool is just taking our queries to the vector database and just converting it into a proper tool that LangGraph can use. All right. We're also providing a name and some description. Description, it's not just metadata. It's really important because this is the kind of information that the agent is going to look at when you're asking something. It's going to say, should I use a tool or should I not? And this is the description so that the agent is going to discriminate. It's going to decide which tool to use. So be sure that you are providing well explanatory and well-documented descriptions here. Okay, so let's define the retrieval tool and let's see what happens if we invoke the tool. So the output is really similar, but in this case, the question is different, but the tool is providing chunks. All right, so this is the output of the tool. If we go back to the diagram of the React agent, whenever the agent decides in the thought, okay, I need to fetch some relevant context from Rosaria's article, it's just going to go to the action block and it's going to use this tool, fetch relevant context from the vector database. Then it's going to observe these retrieved chunks, and inject it into the thought system, into the thought block. And the LLM is going to take all of these chunks, process the chunks, and just provide an actual response to the user. Okay, so let me see where we are at. All right, so yeah, here we are just using the retrieval tool again. And now let's build the actual system that I promised Rosaria and the audience. So we are going to build this React agent for my data guest. So first of all, we're just creating our LLM with tools, and we are using the retrieval tool that we defined that is connected to ChromaDB. We are also defining the memory, as we saw before, the short-term memory, so that my data guest assistant doesn't forget about us in just one turn. We are creating also this assistant node that is going to make calls with the LLM with tool based on the previous messages. And here work as always. So first of all, we are defining the builder or the workflow with the state graph and the messages state. Then we are adding the nodes. First of all, the assistant node, and then the tools node that is going to accept the retriever tool as input. Now it's time for the edges. So we connect the start edge with the assistant edge, and we are adding the conditional edge that is going to use the tools condition. So remember, this is pre-built LangGraph functionality. And finally, and this is the most important step, we are closing the loop. So we are taking an edge that is going to connect the tools node with the assistant node, right? We are compiling finally with the memory checkpointer. And let me show you what it looks like. So the My Data Guest assistant looks something like this. We have start, the assistant, and an end. If I just ask something about Alessandro Romano, for example, it's going to go directly to the end because it's not related to Rosaria's article. If I ask something about Rosaria's article, it's going to go through the tools path and then send back all the information about the relevant chunks. So here you have the final test. We are just passing a configurable, a thread ID of 1 so that it remembers us. And as human message, what are the 3 main approaches to tokenization? This is something that Rosario covers in this amazing article. Sorry, it's in here if I remember correctly. Yeah, subword-based tokenization. So we are going to check what this assistant tells or knows about this topic. So first of all, this is my message. Then the agent understands that it's necessary to call a tool, all right? And it calls the tool, right? It performs an action. The React agent performs an action. This is the tool message that contains the different chunks that are extracted from Rosario's article. So emergent behaviors, still not fully understood, blah, blah, blah. And finally, this is the formatted AI message that we are receiving as humans when we ask about Rosario's article. And in here you can see that it's correct. So word-based tokenization, character-based, and subword-based tokenization, which is accurate, as we can see here. And that's everything. Now, my data guest has to pay me a lot of money because they want to use this probably in their Substack, but this is my property. So sorry for that, Rosaria, but that's not going to happen.
Thank you, Miguel. It was a very useful and very informative and very entertaining tutorial. I think it was the most entertaining tutorial I've ever heard in a long time. So thank you very much.
Thanks to you.
Very,
Thanks
very
for the
nice.
invite. That's
Thank
great.
you. So, yeah, I mean, we have reached the end of the podcast, so there is not much time, but thank you so much. I think it's going to be very useful for the people who follow us to learn how to implement in practice an AI agent using LangGraph. It was actually, I didn't know how to do it, so it was extremely informative. Very nice.
That's great. That's great.
Thank you also for the time that you took to teach us. And yeah, thank you for using my article.
Amazing article. I really enjoyed reading that.
That was now people don't need to read it. They just ask the assistant and they know all the summary.
That's a bit sad. Yeah.
No, it's okay,
but you can count the agent as another viewer, I guess.
Totally. And then thank you to the audience to listening to us also for this podcast episode.
Okay.
Bye.
Perfect. Bye-bye.